All right, so this is our second lecture for ISTM 313 on the 26th of January. We're going to talk through how we model data for organizations and talk through some of the basic principles behind an entity relationship diagram today. And then we're going to start working through some of the problems in the workbook. So let me go ahead and share my slide deck, and we will go ahead and get started. So in terms of how any organization wants to model data that they might use in the organization, really the important question we have to ask is, how does the data work in the real world? And we want our software to model that data accurately. Now, I had this discussion earlier with one of the students in this class, actually. One of the things we've seen over time is that sometimes because of the way our databases work and the way we store information in databases and in computer programs, we have modified the way the real world works to satisfy the way the software wants things to work. So this is not just a one-way street. It'd be perfect if it was, where we just went out and looked at the way the world is working and we made the software emulate that perfectly. But that is not always the case. In fact, in a lot of cases, what we found is if we can modify the way our business practices work just a little bit, we can make some small, subtle changes. We can think about things a little bit differently. That lends itself to how a computer would think about how to store data, how to modify data, how to access information. And then both of them can play nicely with one another. And what it often does is it does lend itself to improving the way our business processes actually work. If we can get the processes to work in a really systematic way, that lends itself to database storage, and then that lends itself to a better process. So this is kind of a back and forth activity where we look at the way the world's working, we model it in the database, we let the database inform how maybe the world should work. We model that in the database. We kind of go back and forth until we come to some sort of equilibrium. So what we're going to attempt to do this semester, at least early on, is do our best to model the real world, to model reality. And to start with, we're not going to let our modeling impact the real world. We're going to let the real world 100% impact our modeling. But as we move through the semester, we'll see that sometimes the software doesn't allow us to do everything we'd want to do, and we might have to curb the way the real world works just a little bit to make it work inside our software. So there are some trade-offs as we move through this from a realistic standpoint. We're going to be using entity relationship diagrams to describe how data behaves itself in the real world and how we might be able to create it in our actual software. Typically, the reason why we're using ERD is it is very easy to use. It does support things like computer-aided software engineering. So once you create these diagrams, you can potentially plug the diagram into a software package, and it can then create the database models behind the scenes for you. You can actually have it auto code things for you, which is really cool. Entities and relationships should be what we quote unquote call natural. They should fit the right way a real world environment actually behaves. So we're going to try to use this diagram model, this ERD model, to reflect real world environments, and it does a pretty good job of doing so. However, there is no standard notation for how ERD works. We're going to be using some common notation you see in a lot of places, but different software packages and different practitioners might use different symbology than what we're using in this class. I'm adopting what Aaron Becker and I have decided is kind of the best common set of symbols, but there are lots of other possibilities that are out there, and there's nothing wrong with them, just like there's nothing wrong with how we're approaching it. So we're going to take one look at it, but if you see somebody else's ERD, you might find that theirs looks a lot different than what we've done. It still probably will make common sense. They're just using a different set of symbols for their approach. Let's talk about the big ticket items for an ERD. The first and foremost, and we talked about this last time, is an entity. An entity is a person or a place or an object or an event or even sometimes a concept. From a mental visualization standpoint, the way I would think about this is, what might you type in to a row in a table on a spreadsheet? If a single row in your spreadsheet has information about a product or about an activity that you did or about you, right? Or the people in your family or the people that are in an organization that you run. Those are entities. Each individual entry in the table is an instance of that entity. So each person you're putting in, or each object you're putting in, or each event that you're putting in, each activity is a specific instantiation of the generalized entity. The entity itself is what you would type in a row in a table on a spreadsheet or on a piece of paper. And so that's kind of the easiest way to visualize what we're talking about here. Relationships are how we think about how entities relate to one another, how they connect with one another. So I can think about a spreadsheet that has a whole bunch of different students on one page. And then on another tab in the spreadsheet, I might have a list of all of the various volunteer opportunities that our group could pursue this month or this semester or this year. And then I can think about how those might connect, right? Each member of our club could potentially participate in a bunch of different events. Each event probably has one or more volunteers that's participating in that event. And so there's some sort of relationship between the two different entities, the people entity and the activity entity. We have to sort of figure out how those different things connect. And there are probably some rules in terms of the minimum number, the maximum number, whether you have to participate, whether you don't have to participate. And so that's part of the relationships. We'll talk a little bit how we're linking these entities together. The third definition, attributes. The attributes are a way we're describing an entity or a relationship. So an attribute might be something like your name or your phone number or your address. It might be the name of an activity, the date of an activity, how long it's going to be. It might be some sort of fundraising goal. It could be all kinds of things that are related to that specific entity. How do we describe what that entity is? And again, the specific entries would be an instantiation of that entity. So a specific person's name, John Smith, or a specific activity, big event, would be specific instances of the entity and its attributes. But the generalized attributes are just ways we're describing our entity or our relationships. Here are some of the symbols that we're going to use this semester. The most important on this chart is that top left corner, an entity. It's just going to be a rectangle for us. Really, really simple. We will potentially talk about weak entities, at least a little bit, but we're going to try to avoid weak entities as much as we can when we get farther into the semester. And I'll talk about what weak entities are in just a second. We will be using associative entities. They're a really clever way of managing certain types of relationships. So you'll see associative entities a lot as we get farther into the semester. If we want to draw a diagram that includes specific attributes, they'll be in ovals, and an oval will be connected to an entity. An attribute has to be connected to the bigger rectangle, and it's just the way we're describing that rectangle. If you see an attribute that has an underline underneath it, that means that it is the unique identifier, something like your UIN or your social security number, or a specific product SKU to identify that product. If you don't see an underline, it's just some way of describing that thing, but it might not be unique. Eventually, we'll talk about things like multi-valued attributes and derived attributes. We can worry about that a little bit later. Third important symbol is we're going to see relationships, which are represented by that diamond. And a relationship is between one or two or more entities. And that's how they talk to one another, how they communicate with one another, how they have a relationship with each other. And eventually, again, we'll talk about identifying relationships. And I will say, this is not my graph. So yes, there's a spelling mistake. I didn't make it, but I also haven't fixed it. It's supposed to say identifying relationship, not identifying relationship. That's a little bit different. So we talked about entities. These are something of interest to us in our database. A person, place, or thing is a good way of thinking about it, at least to start with. always represented by a rectangle. For our simplistic diagrams, they're just going to have a single description inside the rectangle. And then you would have to kind of imagine what that would entail. For our more detailed diagrams, you wouldn't have to imagine it because we draw all those ovals around the rectangle to write down the various attributes that are important to that entity. And these diagrams don't have to be complete. So it might be that I have a customer rectangle and one oval off to the side that says customer ID that's underlined to say, hey, this is going to have a unique identifier and it's called customer ID. Is there more stuff inside the customer entity? Of course. There's going to be their name, their phone number, all that kind of stuff. But maybe we don't write it all down. Our diagrams are meant to be illustrative of what we're trying to represent, but they may not be complete in terms of everything we would need. They get really cluttered if you include every single little fact. So we may have some sketches potentially. On the right-hand side, you can see the instance of a customer entity. So you can see all the specific information we might have about one customer that we would represent inside our database. We typically won't see this in our diagrams. This is just so you can visualize what we're talking about here. Entity types are really just collections of entity instances. So again, think of an entire table full of something, people, or places, or things. An entire table full of those things would be an entity type. An entity instance is a single row in the table, again, trying to get our terminology correct. A strong entity is something that can exist independently in your database. So an individual in your company that is an employee for your company is probably a strong entity that exists all by itself. We will potentially model what we call weak entities that require the existence of another entity to exist in the first place. The best example I can think of is family members for an employee. As soon as the employee stops being an employee for the company, those dependents no longer are relevant inside the company either. Right? We don't pay attention to them anymore because they were relevant only to that employee. So weak entities rely on a strong entity in order to have their own identity. And we're going to try to avoid those as much as we can because you have this rule you have to enforce where unless you have the strong entity, you can't have the weak entity, and that rule can sometimes be challenging. So weak entities are going to be something we're going to tend to shy away from if possible. But again, we're trying to use these diagrams to model the real world as best as we can. So if that's the way the real world works, that's what we're going to model. So we'll see how later in the semester we tweak things a little bit so that we're not reflecting the real world quite as accurately, but we are making the data more secure and more robust and the rules a little bit easier to follow. And so there's this little bit of give and take when we get farther into this material. Entities should be something that has multiple instances in the database. If we were going to create a database for Texas A&M, there wouldn't be a single entity at the very top that just says Texas A&M University, because there's only one of those things. So there's no reason to have a rectangle that has just one thing inside of it. What we would have instead are all of the various colleges that belong to the university. Well, there are a bunch of those. We might model that. Or all the different departments within a college. Well, there are a bunch of different departments in the college. We might model that. So it should be something where there are multiple instances. If it's just a singular object, you probably don't need to model it in your database. It's something that's kind of an umbrella, and we just assume that it's there, that it's above and kind of around everything, so we don't worry about it. We would also expect an object that is multiple attributes, multiple things that describe that particular object. If it's just a singular column, we might be able to include it in a different entity someplace else. We'll talk about that. That'll come up during some of our examples. And it obviously should be something that we're trying to model. I could model all of your pets, but I may not care about your pets from an institutional standpoint. It might not matter to me, right? Or I could model your favorite brand of clothing, but who cares? That doesn't matter to Texas A&M in terms of your shopping preferences. So it should be something that we actually care about in terms of our model, something that's going to inform some of our decisions. Otherwise, we wouldn't include it. Things that we would not include, like I said, overall entities that are singular, things like the user of the database system, typically not modeled inside the database itself. Typically, the output of the data is also not modeled. That's something that we're going to generate using some code and some programs, some queries. and then we'll output it and we'll send it to a report, we'll put it up on a web page, but it's not typically something that is hard-coded and stored inside the database. It's something that we generate when we need it. Attributes, way we describe our entities, usually a discrete data element, some characteristic of that entity that is meaningful for what we are trying to model. If it's not meaningful, we don't include it. Attributes are something that we are interested in. Very straightforward. We're going to see lots of different attributes. We will tend not to pay too much attention to attributes when we're modeling unless it is something that allows us to uniquely identify an instance in an entity. Then it becomes really important. And again, as we work through some of the examples in the workbook, all of this will become illustrated much more clearly. Some of the classifications for attributes. Some attributes might be required. You have to have an official primary phone number if you are an employee for a company. A product has to have a description, right? But there might be some attributes that are optional, where maybe you have a particular classification, but maybe you don't. Maybe you have a fax number, but maybe you don't, because let's face it, it's 2021, and why do we have fax numbers? So maybe we get rid of some of that stuff, yeah? We might have what's called a simple attribute versus a composite attribute. We'll get to that eventually, but composite attributes would be taking multiple pieces of information and blending them into a single word or phrase or something. And sometimes that's an advantageous way of storing information, sometimes. We will sometimes have single-valued versus multi-valued attributes. Multi-valued attributes would be something where I could potentially have 4 or 5 different possible entries for the same column in a table, right? So if you said, what's your favorite food? I don't have 1, I've got 6. That'd be a multi-valued attribute, or I could enter 6 things instead of 1. Multi-valued attributes are kind of tricky. We'll talk about those in a lot more detail much later in the semester, but they are sometimes very realistic, where we've got multiple entries next to a specific instance of an entity. Some attributes can be derived. So we might be able to figure out the cost of a product based upon some other information that's stored, like how much it weighs and how much its cost per gram is. Then we can figure out a piece of jewelry's overall cost, right? We know how much it weighs, and we know that it's made out of gold, and we know the price of gold. We can figure out the cost of that product. So sometimes our attributes are something that we can figure out using a calculation. And if that's the case, we tend to try to avoid storing them. We'd rather just let the computer do the math and calculate it for us when we need it. That's a more effective way of getting that information rather than storing it in our tables. And like I said, in almost every scenario, we're going to have an attribute or attributes that uniquely identify the entries in an entity, and those are going to be really important as we move through this process. So identifiers, ways that we uniquely identify the individual instances inside our entity. Every instance has to have some way of uniquely identifying an entry. That is why you have a UIN here at Texas A&M. Right? We have a unique identifier for you as a student here at Texas A&M. That's why American citizens tend to have Social Security numbers to uniquely identify them, or you have a unique passport number to identify you. It's really important that products, places, things, people have unique identifiers, because otherwise the way we normally describe things would not be unique. There are not many people out there in the world that have my name, but there's some, and I see them show up in Google searches every once in a while. And you probably have other people out there that have your name as well, first name and last name. And so we can't necessarily use that. We can't necessarily use our phone number because our phone number moves around. We don't necessarily want to use our street address because we move. So having a unique identifier for people and places and things is really important from a data structure standpoint. We sometimes talk about candidate identifiers, something that could be a unique identifier for a specific instance in our entity. Just because it can be a unique identifier doesn't mean that it should be. You could have a situation where you have a really small company and you could say the combination of somebody's first and last name is the unique identifier. And at the moment, we have no situations where that combination isn't unique. Would that be a good choice? No, of course not, because at some point in the future, you might hire somebody else that has the same name as a current employee, and then the database is broken. Not a good choice. You might think, hey, my cell phone number is the perfect unique identifier. No, it's not, because what happens if you get rid of it, or you lose it, or you're sharing it with somebody else, right? So just because it looks like it could be a candidate doesn't necessarily mean that it should be the unique identifier. And there may be situations where there is no obvious choice for a unique identifier, in which case we should make something up. That is what your UIN is. Texas A&M makes up that number for you because there is nothing else that is necessarily unique to you that we want to use inside our system. We don't want to use your social security number, so we make something else up that is unique just to you. When we diagram unique identifiers, they'll get underlined. You'll see that in the symbology. We want to choose identifiers that don't change no matter what. They don't move around, product moves around, anything along those lines, and also are not going to be empty or null. So every instance in that entity will have a unique identifier that only belongs to that product, that place, that thing, that event, and never anything else. And we want to avoid what's called intelligent identifiers. If they contain locations or people or anything that might change in the real world, don't use it as a unique identifier. Not a good choice. We'll eventually talk about this substitution of long composite keys when we get farther into the material. All right, so a quick question from Nathan Howard. He's asking, what do you mean by saying that an attribute could be a key? Does that just mean there could be an option to be a unique identifier? Exactly. I might look through my database to see if there's anything about our products that looks unique, but you have to use then some common sense. It might be, you could look through a list of all the different products that your company sells and says, you know what? Every single one of these products has a unique price. I'm going to make price the unique identifier. That'd be a terrible choice, right? Just because it happens to be unique in your current set of data doesn't mean that it's the right choice for uniquely identifying the product. When somebody says, I want the product that costs $89, you don't want that to be the way you go find that product on the shelf. That'd be a terrible choice. You'd want something that is unique to that product that will never change and would never be given to anything else in our tables, in our entities, in our database. So some sort of code. You think about, you go to Amazon, you have that unique code that belongs to every single product. And if you share that with somebody, they can find that product in Amazon's database, and there's nothing else that compares to it. There is one product that belongs to that unique code. So that's what we're thinking about here. Good question, thank you. All right, once we wrap our head around entities and attributes and unique identifiers, we then need to talk about how our entities relate to one another. So a relationship is some sort of association between the instances of one or more entities. It is possible for an entity to have a relationship with itself. And that's not supposed to sound as bad as it sounded in my ears. It's possible for an entity to have some sort of relationship with other instances in that entity. So for instance, if I had a list of all the employees at Mays School of Business here at Texas A&M, the employees on that list could be the supervisor for somebody. They could also be the employee of somebody, which means each instance might have a relationship to somebody else in that same table. So I have a boss who is in the employee table, but he's also my supervisor. And he is a supervisor, and everybody's a supervisor until you really get to the dean, right? The dean is the only person in Mays Business School who doesn't have a supervisor in Mays Business School. So that's one entity, employees, but there's a relationship between some of the instances and some of the other instances in that same table. We can have relationships, of course, between multiple entities. So we've talked about students and classes. There's probably a relationship between students and classes, where students take classes and classes have multiple students enrolled. So we can talk about how many entities are involved, and typically we're going to be talking about one-to-one relationship between one entity, or two entities that are connected to each other somehow, or sometimes three entities that are talked about. That's about as big as we're going to get in this class. And even when we have three, we're going to have to do something about that. That's kind of challenging. We're also going to talk about cardinality. And that's better done with some symbology. So let me wait until we get into some of these later slides to talk about that. So in this class, the only relationships we are going to talk about are a relationship between an entity and itself, a relationship between one entity and another, and a three-way relationship between three different entities. So a unary relationship is the employee example I just gave you. Binary relationship is two entities that have some sort of connection with each other. And a ternary relationship is something where there is some sort of three-way conjunction between different entities. And I'll give you some specific examples that'll help illustrate these. But the terms, unary, binary, and ternary, the most common that we will see this semester is a binary relationship between two different entities and how they talk to one another. Binary is by far the most common. The cardinality of relationship. What kind of relationship between the various entities? One-to-one is that each entity in a relationship will have exactly one related entity. Most organizations will have a rule that says you have one supervisor you answer to. Now, I always think of the classic movie Office Space, which every business student should watch, where the main character talks about the fact that he has 8 different bosses. That's a terrible organizational structure. Most organizational structures will require a one-to-one relationship, or sorry, it's really a one-to-many, but a one relationship direction where I have just one supervisor. Now, one-to-many would be what I'm describing, which is I have one supervisor, but in the other direction, a supervisor might have lots and lots of employees. Yeah. The one-to-one, I'm just sort of thinking ahead here. The one-to-one is each employee has one office, and each office has one employee. That's not true of all organizations, but let's assume we have an organization where every single person gets their own office. They don't share an office with anybody, and they have to have an office in order to work in the business. So it's a one-to-one relationship. Each office is assigned to a person. Each person is assigned to an office. That's one-to-one. One-to-many would be each supervisor might have lots of employees. Each employee only has one supervisor. Many-to-many. Each class has lots of students. Each student takes lots of classes. Many-to-many relationships. And then finally, cardinality constraints. We might limit the minimum or the maximum. Minimum cardinality is either a 0 or a 1 most of the time. 0 would mean that it's optional. You don't necessarily have to participate in a relationship, but you might. 1 would be you absolutely have to participate. So that's for minimum cardinality. For maximum cardinality, it might be 1 or it might be more than 1. Right? So it might be, if you participate, there can only be 1 participant at most, but there might be a situation where you have lots of participants. So lots of interesting things we can do here from a cardinality rule perspective. And here are the big ticket items you would expect to see. You could have a mandatory 1. I am going to be assigned to an office. I'm only assigned to one office, but I have to be assigned to one office. You could have a mandatory many. For a class to exist at Texas A&M, there has to be a minimum of 1 student enrolled. There could be 2 or 3 or 5 or 50 or 100, but there has to be at least 1. So that'd be the second example of mandatory many. At least 1 entry, but there might be lots of entries. Another really good example of this is an order. If you are creating an order in a database, I'm going to go buy something online. I have to be buying at least 1 product for an order to exist. Might I be ordering 10 different things and different quantities of those things? Absolutely. But in order for an order to exist in the first place, I've got to be buying something. So minimum 1, maximum many. Optional 1. The example I gave in the last lecture was an assigned parking spot. I don't have one, but if I had one, I'd have 1. Yeah. So it's optional. You may not get 1, but if you do, the most you have is 1. And then optional many. Maybe that you have a situation where there doesn't have to be any, but there could be a lot, right? That's the most flexible, kind of the most generous is you don't necessarily have to participate. If you do participate, there might be lots of participants. So optional many. We'll talk about all these cardinalities in terms of how they work in a real world environment when we get into our workbook examples today. I'm going to briefly talk about this. If the associative entity doesn't make sense to you today when I'm talking about it, Don't worry about it. It often takes multiple examples of associative entities before they make sense to students that are first seeing this database example. So don't sweat this slide if after I talk about it you say, yeah, I didn't really understand what Tim was talking about. In this diagram, what we are suggesting is that products can belong to multiple orders and orders can contain multiple products. And that makes sense, right? If I have a bunch of stuff in the warehouse, it's absolutely possible that an order from a customer could come in for lots of different products. And we would also expect that products could be shipped out to multiple different orders. So this relationship is effectively a many-to-many relationship. Okay, now I want you to pause for a second and just visualize in your head how you would store the information for orders and products and how they relate to one another. So for orders, it would be customer that is ordering and it's order number 1 and they're ordering 5 of the red doodad and they're ordering 7 of the Gidget and they're ordering 23 of the doodad. You can kind of imagine what that order might look like. For products, it's going to be the product name, the product description, some sort of unique identifier, its cost, its price, its weight, its storage location, all those kinds of things. You can imagine that, right? But think about how those go together then. Where do you store what's being ordered and how much is being ordered each of the different products? It gets to be kind of complicated, right? Because an order is supposed to be a single row in the table, but it potentially contains lots and lots of different products as part of that order. A product is supposed to be a single row in a table, but that product might belong to 16, 123 different orders. I don't know. So where do you store that information in terms of how they are related to one another? And the way we typically solve this when it's a many-to-many relationship, like you're seeing here, where these many-to-many, and I always hold my 3 fingers, these are what we call crow's feet, if you're old school database diagrammer, because they kind of look like the feet of a bird. If the crow's feet are pointed outwards towards both of the entities, it becomes really hard to model how you'd store this information. So what we do is we flip the crow's feet around, we point them inward instead of outward towards a new rectangle, but you'll notice this is a rectangle with a diamond on the inside. And if you go back to an earlier slide, this is a specific object. It's called an associative entity. It's not an entity that would exist all by itself. It's an entity that we would make up in the database world to serve a specific purpose. It is the combination of one side of the equation and the other side of the equation to allow a many-to-many relationship to exist. And think about how this works. For the order line, this table on the inside, it really would potentially just have a couple of different entries. Each table entry would have a specific order number, and then it would have a specific product ID, and then it might have something like the quantity of that product. The next table entry might be the same order number, but a different product and a different quantity. And then the next one would be the same order number, a different product and a different quantity. So think about looking at kind of like your receipt that you get when you're buying a bunch of different things or you're getting parts replaced in your car or something like that, right? Think about what it looks like. It is all on the same invoice, same order, right? The whole big piece of paper is one order. But then inside it are all the line items, which are you got 2 of these gaskets and 3 of these nuts and 24 of these bolts and an hour of service, right? So each line item is a specific thing and some quantity of that thing. That's what order line would serve. So the order line, each entry in the order line can only have one order number and can only have one product ID. So going out, it's a mandatory one and a maximum one. Has to have a 1-1 relationship there where you have exactly one order ID and one product ID per order line, and then probably some additional information as well. In the other direction, can an order show up multiple times in our order line table? You bet. That would mean that that order has a bunch of different products in it. Can a product show up multiple times in the order line table? Of course, that would mean that that product is being ordered in different orders throughout the history of our company. Absolutely okay. Okay. But that table in the middle, we kind of manufacture to have a place where you have those one-one relationships over and over and over and over and over again. A place to store where the order and the product come together in a regular fashion. This is called an associative entity. Again, if this first time I talked about it, you went, yeah, no, that's okay. I promise we're going to keep talking through these examples, and eventually, for most of you, hopefully all of you, but most of you, the associative entity will start to make more sense. It's an unusual thing. It's really important to databases, but the first couple times we talk about it can be really confusing. This is the kind of notation that I'm going to expect to see as we move through our examples in class. Sometimes we'll see these ovals, and we'll specifically see ovals for underlining our unique identifiers. So they'll be handy, but you don't have to have an oval for every single attribute. That'd be totally okay if you left some of them out. We will absolutely see our rectangles with the name of the entity inside of it. And typically it's going to be all capital letters if you want to be a stickler for this sort of thing. We're going to see relationships between our entities. And what I'm going to want to see early on when we draw these relationships is the cardinality. Is it one-to-one or one-to-many? Or potentially many-to-many, which we're going to then adjust. And I'm going to want to see the mins and maxes. And we're going to have some discussions because sometimes there's going to be some room for interpretation in terms of minimums and maximums. So in this case, you can see that a customer submits orders. Can a customer exist in our database without ever ordering anything? Yeah, I can sign up for a company webpage and then decide never to buy anything, and I'm still in their database. So there's a minimum of 0 in terms of how many customers participate in orders. But can a customer provide many orders? Yeah, absolutely. So there's a maximum of many in terms of the customer participating in the order process. Yeah. For an order to exist, how many customers belong to that specific order number? Has to be 1, can't be more, can't be less. This order was ordered by this customer, nobody else. Order can't exist without a customer. Order can only exist with 1 customer. Now, you might say, oh, we've got a situation where at our company, multiple customers could get together and order something together. Different model. Terrible model, I might suggest, but different model. In this model, the way I'm reading the diagram is that an order belongs to only 1 customer and has to belong to 1 customer. So I'm going to be looking at the picture and reading it out, and then we have to decide whether it actually reflects the real world or not. In this case, an order has to have exactly 1 customer. That seems pretty realistic to me. In this case, the unique identifier for a customer is the customer ID. The unique identifier for an order is the order ID. But part of an order is also a customer ID. Notice the customer ID and the customer ID are in 2 different places. In the order, the customer ID is not unique because the customer can place lots and lots of orders. So I might see your customer ID in my order table 16 different times because you've ordered 16 different times. Totally fine, that's no problem. Doesn't have to be unique because it's not the unique identifier for that table. So this is some of the symbology we'll be seeing as we move through the semester. Some alternative notation you might see in other examples. If you go out and Google things, or you read other textbooks, or you've taken other classes, you might see something like this where it doesn't have the minimums and maximums. That's fine. We're going to try to add that information if we can, at least early on, because I think it does inform some of the information we're thinking about. You might see asterisks instead of underlines to identify the unique identifier. So the asterisk next to customer ID and the asterisk next to order ID, slightly different symbology. We can make sense of that. We're all pretty smart people here. You might see some pound signs for unique identifiers, and then asterisks for required fields. This is how Oracle does it, just to confuse things a little bit. We're not going to be using the Oracle notation, but if you have parents that have dealt with Oracle, or you've done Oracle work in an internship or a job, the symbology might be slightly different. But again, it's trying to accomplish the same goal here. Okay. Eventually, we might talk about some of these topics. So things like time-dependent data, typically what you see is a lot of repetition in the data, and the unique identifier is the timestamp itself. I don't think we're going to spend much time doing any kind of timestamp data, but you can imagine some sort of log of events that are happening inside a system. And the unique identifier is the time and date, right? Everything else might repeat over and over and over again, but the unique time date stamp is what's unique in the data. We might see more than one relationship between the same entity types. We will actually deal with that sometimes, where there's going to be a one-to-one relationship between a table and a one-to-many relationship between two different tables. And we'll have to talk about the rules for both of those. That does happen sometimes. We might also talk about hierarchical relationships where we're modeling the hierarchies we might see in a company, something like that. They're always just modeled as one-to-many. So they don't have to be anything complicated. And they are fairly common in the real world. So we're going to see some hierarchical relationships in our databases potentially. I don't want to talk about weak entities with identifying relationships, but I wanted to include it in the slide deck because we will eventually come back to this and talk about this challenge here. And it might come up during some of our workbook examples as well. But weak entities with identifying relationships are interesting. They're tricky. So we might eventually come back and talk about that. All right, so that's my spiel on some of the symbology and the terminology we're going to be using for ERD. So next is we want to talk about some of the early examples in the workbook. And I'm opening up my workbook right now. Hopefully you guys have it open and ready to go. And we're going to talk through just the first couple of these today. We'll see what we can get through. And as promised, I'm going to randomly pick on some people. So the first person I'm picking on is Javen Reed. Javen, are you here today?
Yes, I'm here.
Great. So I'm going to ask you to work through this first problem with me. Let me go ahead and share it on my screen and talk about it. And then I'm going to have you share your screen and we'll try to work through it.
Okay.
So this first problem, pretty simple, but we have some things to discuss. A student can take several courses. Each course has many students. So, how do you think we should draw this picture? Javen, you can share your screen if you'd like, and we can talk about what you came up with for a solution.
Okay, so I thought this was many to many, and I wasn't able to use the program that you suggested. So
yeah, we need to talk about that. So I'm going to interrupt Javen for a little bit. Were people able to sign up for the education version of the software, Lucidchart? Some head nods. Did it give you access to some of the ERD symbology? I had one student say that it didn't. I see some people that are nodding their heads though. Okay, give it a try. If you're having trouble with the Lucidchart stuff, please feel free to schedule a meeting with me at some point, or I can try to schedule some sort of outside of class time where we can all kind of get together and share our screens and see if we can figure this out. You should have access to that, but you don't have to use it. Okay, Javen, what do you got for us?
Okay. Okay, can you see that?
I can.
Okay, so after your presentation, I realized that this is wrong, but
it is right. There's just a way we're going to adjust it. So what did you come up with?
Okay, so I thought it was many to many since each student can take several courses and each course can have many students. So I put optional for a student, the little circle to represent optional mini, okay. And then put mandatory mini for the courses because each course should have to have more than one student. And then I put the lines at the bottom for the student, indicating that the student would be in multiple courses, but you just...
Right, so already, this is great. Already, Javen is noting that when you get to this many-to-many thing, right, and again, I'm doing my crow's feet kind of pointing out, the picture doesn't lend itself to what you're trying to represent. It's kind of a challenge, yeah? So, Javen, now that I've given my talk, what do you think we might want to do differently?
So I think the lines going off student shouldn't be there since you said that would only indicate one student per course, I think, from my understanding.
Okay.
And then I don't know.
That's okay.
I just know that part.
I wanted to give you a shot. You're doing great. Let me ask our second person here. Hold on a second. Allison Campbell, are you here?
Yes, I'm here.
Great. Allison, looking at the picture that Javen provided to us, what do you think we should do to adjust this?
So yes, it's the many to many from what we went over in class today.
Mhm.
I would say, do we need the lines at the bottom, first of all?
The ones with the little circles there at the bottom?
Yes.
No, probably not.
Okay.
So we could probably already just kind of, and that's easy enough. She could just eliminate those. They're kind of extraneous for sure.
Right. And then, so a student can take just one course. So,
Is that true? How many classes have you taken this semester?
well, it could be not a full-time student. Isn't that true?
They
I mean, I'm
could
taking
take a
many,
minimum
but
of, I don't know. I mean, if you're going to put them in the database, is there a minimum of one? Or do we have students that maybe take a hiatus, so there's a minimum of 0?
they probably could take a hiatus and still be considered a student.
But on the
So,
other side, could you take more than one class?
well, yes.
Absolutely, right. So I think going towards the courses that students could be enrolled in 0 or 1 or more classes. What about on the other side?
For this, so the course has to have at least one student.
I would think so, right? A course
Yeah,
doesn't
you
exist
can't,
without a student.
otherwise there's no course.
And honestly, this is where we're again, and you're going to inject some real world examples here. I think the minimum during like the summer, for instance, I believe for my classes has been 10. I have to have at least 10 students or the class doesn't make. I don't know what it is during a normal semester. But let's just say from a database standpoint, a class has to have at least one student and might have to have a lot of students, right? Sure.
Mm-hmm.
Okay. We got to figure out how to draw this differently though. Let me rope in one more person. Rishi Subramanian, are you here? Rishi, are you here? No, Rishi. Okay, Haley Joseph.
I'm here.
Great. Any suggestions as to what we might be able to do to this diagram?
Well, in class, we said when we want a many-to-many, we have to have the associative entity between the two.
Absolutely. So in this picture, we're going to need to flip this thing around a little bit. Instead of the crow's feet going like this, we want the crow's feet going in, and we want to draw a new rectangle in the middle. And Javen, I don't know if you want to try to draw this yourself, you absolutely can. You want me to try to draw on it, I guess I can too.
Okay.
But if you want to try to do this, we want to add yet another box there in the middle. And it would be basically the enrollment box. Okay. So eventually she's going to flip her little crow's feet around. You don't have to do that for right now, but a new box in the middle. And the box in the middle is going to be, I would suggest, enrollment. And it's going to be a box, but it's also going to have a diamond in the center. So I know, unfortunately, since we are online, that drawing is really cumbersome in this class. Yeah, but let's just at least get those two symbols there. That'd be great. So I don't know if you can do the diamond. I see it in basic shapes, top row, third from the right.
I can't find it.
It's on the top row of basic shapes. It's a go down, down, and to the right, 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 to the right. Keep going. That's not a diamond. We'll pretend that is. That's fine.
Sorry.
This center, that's totally fine. This center thing is what we call an associative entity. And again, imagine that she's then redrawn it where the relationships go in. In the center, we would really, all we need are two different columns. It's going to be student ID, course ID. And what is that? That's a particular student is enrolled in that particular course. And then what would be the next row in that table? student ID and course ID. A student is enrolled in a different course. And then what's going to be the next one? Student ID and course ID. And what's going to be in there? A different course for the different student. So this enrollment table is going to have two columns. One is going to be a bunch of different student IDs. One's going to be a bunch of different course IDs. What's unique in that table? I'll open it up to anybody. What's unique in that table? Can students show up more than once in the center?
So it'd be
It
like
should
the
be this
Enrolled in more than
UIN
one
is
class?
unique. Like if the student had a UIN, like
Yeah, so UIN, let's use UIN instead of student ID. Can the UIN show up in the enrollment table in the middle more than one time?
Yes.
Yes, Clay is chiming in. Clay, what would it mean if a student's ID or UIN showed up in the middle more than once?
It just means they're taking more than one class.
They're taking more than one class. Can a course ID show up in that enrollment table more than once?
Yes.
What would that mean?
There's just multiple students in the class.
What is unique in that center table?
Like the nothing.
could I chime in on this one?
Please.
Is there a combination of the student ID with that course ID that becomes
Yes.
one new number?
You got it.
Okay.
Gold star, good job. The uniqueness is the combination of the two things. It's not one thing by itself. But think about it. If I say out loud that you are enrolled in ISTM 313, do I then need to say that you are enrolled in ISTM 313 and also you're enrolled in ISTM 313 and by the way, you're enrolled in ISTM 313? No. I only have to say it once. And in fact, I can't say it more than once because you can't be enrolled in the same class 4 times. You're enrolled once or you're not enrolled at all. The uniqueness of that inner table is that you are enrolled in a class or the class has you as a student that's enrolled. A student can't be enrolled in a class more than once. A class can't have the same student more than once. It's the combination of those two features. Does that make sense to everybody? This is a big idea.
So Professor, I guess just real quick, the associative entity in the middle is what allows us to create this mixture of the two.
Correct. What an associative entity does is it allows us to take that many-to-many relationship and store it effectively in our database. And it's storing exactly that relationship. What are you trying to enforce? That a class has multiple students or that a student takes multiple classes, right? And if you look at that table and you said, well, I only want to see stuff that belongs to Haley Joseph, well, then I'd only look up her UIN and I'd see the 3 or the 4 or the 5 classes that she's enrolled in. But what I can see from a university standpoint is every student that's enrolled in every single class, right? And the database is meant to be this big thing that stores every class, every student, and all the enrollment. And then could we write questions that said, how many students are in ISTM 313? Well, I'd find its unique identifier and I'd find all the students that are enrolled. Or how many classes is Elise Dobos enrolled in? Well, sure, I could go look up her UIN and I could find all her classes. But the table itself would be every student enrolled in every class. And you can only be enrolled in each class once, and each class can only have a singular student enrolled one time.
Okay.
Does that help? Does that make sense, folks?
Just
Awesome.
to confirm on this one,
Yep.
are both of them supposed to have like the circle for the optional many?
That's a great question.
Like
So
the
from that,
crow's foot and then the optional many? Or did we
From that-
decide that
from that-
one was like a mandatory many?
right. So I would say that the crows, hold on. My internet connection was unstable for a second, so I paused. I would say that the crow's feet is mandatory. You have to have the crow's feet on the inside that says each student can show up many times and each class should show up many times. I'm going to suggest the way we described it is the student doesn't have to show up every single time. So next to the crow's foot moving in, there's an optional. The student may not be enrolled in any classes. They're not taking summer classes, for instance. A lot of you don't take summer classes. You're still students at A&M. So an optional for the minimum, a many for the many, pointing in from the student towards the associative entity. In the other direction, the way we talked about it is each class has to have at least one student, but might have many. So a mandatory one. And in fact, we might even write a little notation in there that says mandatory 10, right? Got to have at least 10 in there or you don't exist as a class. That might be a rule. Going the other direction with associative entities, for there to be a row in that middle table that has a student ID and a course ID, going the other direction, has to have one, can only have one. So I'm drawing two ones. I know I'm holding up two fingers. It's a 1-1 thing where there's a minimum one and a maximum one going the other direction towards the outside entities. Because inside table has to have exactly one student per entry and has to have exactly one course per entry. If it doesn't work. Does that make sense? Maybe sort of, kind of, if you're shaking your head and then thinking, yeah, I'm only pretending, so I'm just going to do this until Ted moves on to the next question. That's okay. We're going to keep going and we're going to talk about some more of these.
I have a question about the associative entity. So with their unique identifier, it will always be a matching type of thing. So it'll always be, like for our example, a student with a course. So every associative entity always has like a matching from each side.
It will have to have a matching from each side in order to exist. That's correct. That's right. All right, let's take a look at number 2. I think we can get through one more of these today. So this is great. An instructor can teach several courses, but each course is taught by one instructor. And Jacob Jennings, are you here?
Yes, I'm here.
All right, you are up. Feel free to share your screen and let us know what you think of as a solution for this problem too.
Is it showing up?
Yes.
Okay. I put a option mini for instructors, and for the course, only one instructor for that course.
Right, so if we look at the instructions for this one, an instructor can teach several courses, but each course is taught by exactly one instructor. So again, this isn't necessarily the way all courses work or all universities work. Some classes are team taught. But based upon the description we were given, are we happy with the answer that Jacob gave to us? Does it make sense to everybody? So each course, if you go down towards instructor, has to have one instructor and only one instructor. Absolutely has to have an instructor. Going the other direction, does an instructor have to teach any courses? I guess not, right? Maybe an instructor exists, but they're currently not teaching this semester. Again, I don't teach every summer session. I usually teach one of the 2 summer sessions. So there's some sessions where I'm not teaching. Could I teach multiple classes? Yes, and I almost always am. So this seems like it's reflecting things properly. No need for an associative entity, anything like that. Now, I'm going to jump outside of the diagram just a little bit, just to explain things, but this is outside of the diagram. The way that we would actually probably store this information is we would have instructor information that would have things like the instructor's name, their phone number, their address, right, their office space, and a unique instructor ID over in the instructor table. In the course table, we'd have unique identifier for the course name, the credits, all that good stuff. In the course table, we would also have an additional column that says instructor, and we would see the instructor's ID show up in that column. It has to have a single entry and only one entry. Could an instructor's ID show up in the course table more than once? Of course, because they're teaching 5 different classes. But does it have to show up in that column? Yeah. So that'd be a column that's required, and it has to be information that matches up with the instructor table. You have to look up an instructor's ID and fill it in the course table. That's how the data would actually be structured behind the scenes. That's beyond the diagram, but some of you are probably thinking about that a little bit. So worth at least talking about. Okay. So good. Jacob got the easy one. Everybody else got the hard one. Good job on this one. Thank you guys for that. we are going to pause here. I think even though we have a couple more minutes, I think this is a good place to reset our brains a little bit. We're going to keep working through the workbook. So we're definitely going to get through 3 and 4 next class, but then we're going to try to work through some of the bigger ones. So you can see the problems get a lot larger. So for next class, I want you guys to at least look at 5, 6, and 7, because we're going to try to work through those together as a class. What I might do, again, we're kind of figuring out how class works, but you guys feel free to chime in. I think this might be a good way to do it is we can work through 3 and 4 together, where I can cold call some people and ask you guys to provide your answers, and we can kind of talk about it if we have any discussion. And then we can do some workout breakout rooms, where I can have you guys break out in rooms and work on those bigger problems together, and then kind of come back together as a class and come up with our solutions. I think that sounds kind of like the best way to do it, because you guys can pre-work it a little bit between now and Thursday, and then work on it more together with your group, and then you guys can present kind of the best of your group work to the class, and we can talk about it. Does that sound like an okay plan to everybody? Okay, cool. How did today go? Any feedback on yes, no, good, bad, anything? Because again, this is kind of my first time doing this synchronous but collaborative experience. We're okay?
I have a question for the workbook.
Yeah.
You post the finalized solutions anywhere after we go through them?
I don't typically post the final solutions. So the idea would be, of course, I'm recording this and I will be posting this video. And for ones that are very clear, you have the answers because we just talked about it. So you should be taking notes as to what the answers are for these sorts of things and then working through them. But I don't typically post them, because the second you post something officially online, it's forever lost to me in terms of a mystery to students. You guys know how things like Chegg work, and so do I. So I'm not posting stuff like that, but hopefully you're here engaged, and then you can go out and watch the videos, you can get those answers. There will be situations where there's not going to be a singular answer. There's going to be some things where there's some room for interpretation, in which case you'll have to use your interpretive abilities to decide what you think the best answer is, and that's also okay.
Okay, thank you.
Yeah, of course. Other questions, comments, feedback?
So just to confirm, you want us to kind of look at and try problems 5 through 7 a little bit, but not necessarily try to finish them on our own?
Exactly right. I don't think that you certainly can draw up the entire thing. And I think it would be good for you to do that. But if you want to look through them and say, yeah, this problem, I am baffled. I'm not quite sure where to go with this. I've at least read it, and here's what I'm confused about. And then I'll meet with my fellow students and maybe I'll get some understanding. I think given that we are still in week 2, that's also okay. What I am asking all of you to do as good Texas A&M students is at least look at the material, right? At least take a look at it. So you're not coming into your group work blank when we meet on Thursday. That's not fair to other students. So as long as you've looked through 5, 6, and 7, I think you've done your due diligence preparing for class on Thursday. Does that sound good to everybody? All right, great. Thank you guys so much for meeting with me today. I appreciate it. As soon as this video compiles, I will put it up on the channel on YouTube. So if there's anything you missed, you want to go back and take a look at it, please feel free to do so. For all my quote unquote volunteers today, thank you guys. I appreciate it. And the rest of you, get ready, because you're going to be on my list later on. And so you'll definitely be hearing from me at some point and put on the hot seat. Thank you guys. Enjoy the rest of your day. And I'll see you all on Thursday.